Hey everyone, welcome to The Explainer. Today, we're taking a deep dive into the hidden scaffolding of human language. Have you ever stopped to wonder how machines actually read, comprehend, and map out the massive webs of words we throw at them every single day? Well, if you're curious how AI makes sense of a tangled sentence instead of just staring at a random string of text, you are absolutely in the right place.
To really ground this, let's look at an absolutely beautiful quote from linguist Lucien Tesnière way back in 1959. He said, "Between each word in a sentence and its neighbors, the mind perceives connections. These connections together form the scaffolding of the sentence." I mean, I just love that metaphor, right? Think of a sentence not just as a flat line of text on a page, but as a dynamic, three-dimensional construction project. The words, those are your building blocks. But it's that invisible scaffolding, the deep connections between those words, that actually holds the whole meaning together.
Now, historically, linguistics leaned heavily on something called phrase structure grammar. It relied on these super rigid rules to break sentences down into constituent phrases. But honestly, there's a big catch. It tends to bury the actual semantic links between words under layers of clunky rules, and it really struggles with languages that have flexible word orders. Contrast that with the dependency parse. This is a total game changer. It creates direct, head-to-dependent links between words, completely abstracting away from strict word order. That makes it literally the perfect tool for highly flexible languages like Czech or Spanish, where a grammatical object might just jump around before or after a verb. It's just a much more elegant, direct approach.
So, this brings us to the million-dollar question at the heart of today's explainer. How do computers actually build this scaffolding? I mean, how do we take a machine that natively only understands ones and zeros and teach it to map out these incredibly intricate structural connections in human language?
Well, here's our roadmap to figure that out. First, we'll look at the scaffolding of sentences. Then, universal dependencies. Next, transition-based parsing, followed by graph-based parsing, and finally, we'll wrap up with scoring the parsers.
All right, let's dive right in with part one, the scaffolding of sentences and how we define the core. You know, every structure needs a solid foundation, and in a dependency parse, that foundation is the root node. Basically, the root node is the central organizing word of the entire sentence, usually the main verb. Everything else in the sentence just hangs right off it. And by definition, the root node explicitly has zero incoming arcs. From this single root, a fully connected tree grows out, which ensures that every single other word in the sentence has one and only one structural head.
And this brings us to a really neat concept called projectivity. When we're drawing out these trees, an arc from a head to a dependent is considered projective if there's a clear path to every word that lies between them. In simpler terms, it just means you can draw the entire dependency tree without any of the lines crossing each other. English is mostly projective, which is nice, but remember those flexible languages we talked about? Yeah, they frequently spit out non-projective trees where edges absolutely have to cross to make any grammatical sense. And as we'll see in a minute, dealing with those crossing edges is a massive computational headache.
Moving on to section 2, let's look at building universal dependencies, or what we can call the blueprint.
So, linguists actually created this massive undertaking called the Universal Dependencies Project, which standardizes these exact structural labels across more than 100 different languages. It's incredible. Take a look here. NSUBJ identifies the nominal subject of a verb. OBJ is your direct object, and NMOD shows a nominal modifier. This means that whether an AI model is parsing English, Basque, or Mandarin Chinese, it's using this exact same blueprint of labels to classify those hidden relationships between words.
Okay, section 3, transition-based parsing. Think of this as the assembly line.
I want you to imagine a highly efficient left-to-right assembly line worker. This worker has a buffer of incoming words and a stack to work on. At every single step, a machine learning oracle essentially looks at the state of the line and barks out one of 3 commands. It can say left arc, which connects the top 2 words on the stack and tosses the second one out. It can say right arc, doing the exact reverse and tossing the top word, or it can say shift, which simply pulls a brand new word from the buffer right onto the stack. The parser acts super greedily here, just snapping words together and shifting down the line as fast as humanly or mechanically possible.
Now, because this assembly line worker is so greedy and so fast, it only makes a single pass. Once a decision is made, boom, it's locked in, it cannot be undone. So to prevent a really bad early mistake from totally ruining the entire sentence structure, we sometimes bring in something called beam search.
Instead of just picking the single best-looking action in the moment, Beam Search keeps a few alternative blueprints or decision sequences in its mind simultaneously as it moves through the sentence, and this drastically improves the final accuracy.
But still, it begs the question, right? What happens when that greedy assembly line does make a mistake it just can't recover from? Especially on those super long sentences or those tricky non-projective ones with all the crossing edges.
That brings us to Section 4, graph-based parsing, where we meet the architect.
If our last algorithm was a fast, greedy worker on the floor, this one is the overarching architect. The architect looks at the entire blueprint all at once. It essentially creates this massive web where every single word connects to every other word, and it scores them all. What it's actually doing is searching for a maximum spanning tree. That's the single perfect path within that massive web that starts from the root and has the highest possible cumulative score across all of its edges. That path represents the perfect grammatical parse.
But occasionally, the architect creates a bit of a paradox, an impossible loop where two words are trying to act as each other's head. Yikes. Enter the Chu-Lu-Edmonds algorithm. It acts kind of like a mathematical pair of scissors. It recursively collapses that impossible cycle down into a single node, recalculates all the scores, and then literally snips the weakest link to break the loop. It is a brilliant, elegant cleanup phase that mathematically guarantees you get the true optimal structure, even when those lines have to cross.
Now you might be wondering, how does the architect even know the score of a connection in the first place? Well, modern systems use something called neural bi-affine scoring. They basically run the entire sentence through a neural network encoder to create rich mathematical embeddings for every single word. Then they apply a bi-affine function. Think of this as a complex mathematical filter that learns exactly how a specific head word interacts with a specific dependent word. And out pops a highly accurate probability score for every single structural connection in the entire graph. It's pretty mind-blowing.
And finally, Section 5, scoring the parsers, the inspection.
All right, so we've built the scaffolding, but now we have to inspect it to see if it actually holds up in the real world. When we evaluate these parsers, we have a few options. Exact match is one, but honestly, it's incredibly pessimistic. Think about it. If an algorithm gets a 30-word sentence perfectly right, but messes up one tiny modifier, exact match scores the entire thing as a total failure. That is not very helpful for engineers. So instead, we heavily rely on labeled attachment score, or LAS. This measures the percentage of words that got both the correct head and the correct universal dependency label. We also use unlabeled attachment score, or UAS, which just checks if the word found the right head, totally ignoring the label. These metrics give us a much clearer picture of how accurate the parser actually is.
It's wild to think about the journey here. We went from incredibly rigid rules to greedy assembly lines, and now we're using deep neural architects capable of parsing the complex, totally flexible scaffolding of any human language. It's truly incredible how far this technology has advanced. But language, as we know, is alive. It is constantly shifting, evolving, and blatantly breaking its own rules. So as our neural networks grow even deeper and more advanced, how will they evolve to map the ever-changing, brilliant scaffolding of human language next? It is a thrilling frontier in AI, and I hope this explainer gave you a really strong foundation to understand it. Keep learning, and I will catch you in the next one.